Okay, I hope this talk is worth the waiting, and I hope I don't disappoint you. Now I have a higher expectation on it. So as I said, I will demystify and mitigate the bias for machine learning over graphs. Okay, so now let's first start with why are we interested in graphs? Graphs are everywhere. First of all, it is a mathematical tool that is used to model pairwise relationships, such as in-flight networks, chemical networks, brain networks, where there are nodes. For example, it can denote neurons in brain networks. And there are edges that are connecting the nodes, such as flight paths between airports, neuron connection in the brain. And there are also nodal features. There are data that are laying over the networks and the graphs. So we can see that while we are always talking about data analytics and machine learning, we really cannot learn from the data very well if we ignore this network or graph structure, because a lot of data that we are faced with are collected from the networks or graphs. Like for engineering, what we're interested in, maybe power grids, civil engineering, maybe transportation networks. Right? And learning over networks has attracted a lot of attention, like network topology inference, anomaly detection, clustering, link prediction. They have found applications in various domains, and there are a lot of works going on in how to model the data in the graph and how to learn how to carry out machine learning tasks over the graphs. And on the other hand side, what we are interested in is bias and unfairness in machine learning. So it is known that machine learning algorithms may lead to biased or unfair results. Okay? And nowadays it is attracting more and more attention, especially with this wide application of machine learning algorithms in various domains, various policy making, ChatGPT, that are all closely related to our lives. Right? So it has been shown that machine learning algorithms has some inherent bias, such as it leads to different error rates on different genders in face recognition tasks, different crime prediction rates, different credit approval rates across genders and ethnicities. And henceforth, it is critical for various applications and policy to pay attention to the potential unfairness and bias in machine learning while we are actually using it. So there has been a lot of work on fairness reduction in machine learning, of course, including Professor Ming and Liu's work. And it has been shown that fairness or bias is a critical issue in machine learning, and we really need to take this into consideration while we are making decisions using machine learning algorithms. Okay? However, fairness over graphs are relatively underexplored, in the sense that most of the works focus on tabularity, which means that there are feature vectors, but there's no graph structure. Okay? And you may be curious, what is so different about machine learning over graphs? Can't we just use existing algorithms for bias reduction or fairness over machine learning to cope with machine learning over networks and graphs? The motivation here is because the fact that there's a graph structure, that the structural information may actually propagate and possibly amplify bias. The reason is because whenever there's a graph, you know that there's certain type of information aggregation or information propagation or collaboration that is going on. This type of graph structure may lead to different effects and even amplify the existing bias in nodal features. Okay, so here the goal of our work is to study how can we carry out fair and accurate machine learning over graphs. Specifically, I will focus on several different techniques. One is graph data augmentation, normalization design, as well as tension design. Okay? And we will see how.
Question.
Yes.
Is the problem to predict a label for each node?
That's a good question. So I should clarify. First of all, you are right. This is one type of machine learning algorithms in over graphs, in the sense that we want to predict or do classification over nodes in the networks. There might be other type of algorithms and tasks. Henceforth, what I am going to talk about is on the unsupervised mode, in the sense that when we are saying that predicting labels that is in a supervised fashion, while what I will focus on is more on unsupervised fashion, in the sense that we learn the representation and the representation can be used for ensuing tasks as well. So, but you are correct that this is one type of task that is in machine learning over graphs, and we will see experiments on mainly node classification tasks. Does that answer your question?
Yeah.
Sure. So let's first look at what are the potential source of bias in learning over graphs. So first of all, graph structure itself has intrinsic bias, in the sense that we know that, for example, in social networks, we tend to make friends with people who are more similar with each other. That's henceforth, there tends to be higher probability of connection or higher density of connection among nodes that are from the same sensitivity. Here, sensitive group and denotes, for example, female, male, or Asian, white, type. So if the real world network exists in such type of correlation, meaning that we tend to have more connectivity, more edges that are connecting me with the, for example, B, then learning, when we are carrying out machine learning tasks using such a graph structure, it necessarily amplifies already existing bias that are in the networks. And it also leads to indirect use of sensitive attributes in training. Because even if I don't know the sensitive attributes, even if it is not revealed when we are training a machine learning model, the fact that that same sensitive group tends to have more inter-edges than inter-edges, kind of intrinsically reveal this image. Okay, and there has been some fairness-aware learning in graph domain, but most of them are designed for specific learning tasks or frameworks. For example, there is adversarial training, and they lack a rigorous analysis in the sense that usually we just train up adversarial networks and try to mitigate. Okay.
I have a question.
Yes.
So you're doing this over homophilic graphs. Like you're assuming that a node's neighbors are more likely to be of the same class. Is that like a prior assumption you're making, or is that like an example? Like, can this work on heterophilic graphs as well?
So it is not an assumption. It can be used in any type of graphs. It is just an observation of potential bias.
Okay.
But the fact that the connectivity may be density may be different within or across group is the key problem.
Right.
As we will see later in the analysis, it can also be used. So we will provide theoretical analysis for source of bias in graph neural networks, and we will develop adaptive augmentation design, and which will provide us explainable and scalable bias reduction. Okay, so this will just give you a preview, but it will be clear later. So let's first see that example of real-world networks about whether this kind of connectivity unbalance really exists in real-world networks. So here I show an example of Facebook-like real-world social networks. And you can see that specifically, let's focus on the intra-group edge versus inter-group edge. So you can see that especially in this social network, there are considerably more intra-group edges than inter-group edges, okay? Meaning that the edge density is indeed much higher when we are in the same sensitive group. In this specific case, I think the sensitive attribute denotes the gender, so people tend to make more friends. Okay, so there's a higher probability for connection between similar users. So the first idea is to design an augmentation scheme to balance the connectivity. So we say that if this is the problem, then can we just design a sampling scheme to just augment the data? Augment the data means to just change the data, sample the data, manipulate the training data to balance out the connectivity. So this is a very intuitive design. We just want to test it out to see how it works. Okay, so there are different criteria like dynamic fairness, where SI and SJ denotes the sensitive attribute of node I or node J. For example, it can be female or male. Okay, and AIJ denotes whether there exists an edge or not. So we say that what are the criteria that we want to develop to kind of balance out? The first thing that we could think of is to say whether there is an edge or not should not depend on whether they are from the same sensitive group or not. Another criterion would be, in addition to whether the sensitive attributes are same or not, we should look at exactly what the sensitive attributes are. And a fair, more fair data set should be the fact that the edges are more balanced regardless of what is a sensitive attribute. In addition, we know that in graphs, sometimes in addition to edge connectivity patterns, higher order connectivity patterns, such as a triadic closure, neighbors of neighbors are also neighbors with each other. This type of triadic closure if all three nodes are from the same sensitive group, then it is likely to introduce more. Okay, so this is just intuitive design to propose certain criteria so that we could augment it. Then based on these criteria, as you can think, we can just sample from the network edges, network connectivities, and generate a different version of it. Okay. So we tested this intuitive algorithm, and the performance metric is the accuracy of node classification. And the fairness metric is the statistical parity and equal opportunity. Here, S denotes the sensitive attributes, Y hat denotes the estimated label of the particular node. And then this statistical parity basically denotes the discrepancy among positive rate, while equal opportunity, as you can see, that it characterizes the discrepancy in terms of a true positive rate. Okay? So these two criteria should be the lower the better. Okay? So here's the result. Let's just first see these highlighted part. So this last three lines are the proposed algorithms based on different fairness measures to just delete some edges. Okay, and first of all, what we can see is this grace is the benchmark is of the proposed algorithm. Basically, it's a fairness agnostic, while DGI, GCA, and the NIFTY are fairness aware counterpart, as well as this fair work. So as you can see from here, which may be a little bit too small, but the fairness-aware algorithm provides similar accuracy, while better fairness measures in the sense that these delta SP and the delta EO are lower. Okay.
So just to clarify, with the fairness metric, basically you just want the model to ignore certain properties, like these sensitive features, you just basically want it to give the same answer no matter, or to have the same probability regardless of what the actual feature value is.
So white hat here is the estimated label. So you can see that, for example, equal opportunity is the similar true positive rate, meaning that if y is equal to 1, y hat is also equal to 1. So they want to make the discrepancy in terms of a true positive rate the smaller. Make sense? Yes.
I noticed that your baseline is always in like D4. Have you ever tried like massive transmitting network like GCN?
In this specific work, so here you're right. This is a random walk-based method. These are neural network-based method. These 4 baselines are GCN-based method. For example, yes, first is DGI. And for example, GRACE is a graph contextual learning based on two-layer GCN.
GCA, what is that GCA?
GCA.
Attention.
No, it's a graph, also a graph contextual learning method. I don't remember exact name, but they are both, all these 4 are contextual learning based methods.
Okay. Yeah. So the basic idea is you have graphical data, you have a learning task.
Yes.
You want to change, you augment the data before you do the learning, right? That's the idea. You're going to talk about how you change, how you do the augmentation, or did you already talk about it? The augmentation part.
Yeah, sorry. I actually skipped that part in the sense that the augmentation part is inherited here. Basically says how many edges that I should sample that they are with the same sensitivity.
Okay, so you use sampling to compensate for the disparity.
Exactly.
So that if you look at the sampled data, they look uniform. Okay.
Yes, you're correct. Sorry, I should have mentioned that here the criterion are used to sample the edges, or in other words, delete the edges to balance the data. And this is the result. So you can see that we provide improved fairness metric with similar accuracy. And in addition, we see that triangle-based edge deletion provides much better fairness metric in this pocket N data set, which means that the subgraph structure is indeed quite important. So, however, I just provided an intuitive argument that I should keep my promise to explain to you what are the source of bias, to demystifying it. Okay, so the question now is, can we explain the source of bias? Okay, even though this intuitive design provides promising results. Okay? And we want to look deeper into what is the reason that actually there's a bias, because we know that the sensitive attributes are not directly used in the training, right? So let's look at a simple graph neural network design. Okay, and here are a lot of notations, and let's not focus on it. Just remember, AIJs are denotes whether there's an edge or not. And because I don't want you to look at it, I will make it disappear. So now I just want to first look at this equation. What it basically says is that this edge here, this edge here is the representation at the L minus 1th layer. Okay, and the HL is the hidden representation at the L's layer of a graph neural network. So the difference of graph neural network and the conventional neural network multi-layer perception is in the sense that the graph structure influences how you aggregate the hidden representation in each layer. You can see that here the W is just the graph neural network weight. The key difference is you are aggregating the neighborhood representation in each layer. It's Ni denotes the neighborhood of node I. Okay, which in this figure, what it says is that if I'm an input graph, it looks like this, and if we look at node A, which is this node, then the representation is just aggregating the representation from the neighbors B, C, D, and pass it through a non-linear activation function. Okay, so you can see from this figure where I covered the nodes differently. Let's think about if blue and green denotes two sensitive groups, female, male. Okay, then if the graph really has this structure information, says that if I'm blue node, I have more neighbors that are blue nodes. Then if I aggregate the information in each and every layer of graph neural network, it means that eventually I will aggregate more and more information from nodes that are from the same sensitive. Okay, and that is the reason why, even though sensitive attribute is not used, but the graph structure may amplify already existing bias. Okay, but in addition to the figures, now we need to put it some mathematical equation to show that it is rigorously analyzed. So that now let's measure the correlation between aggregated representation and the sensitive group. Okay, and we measure the correlation of the aggregated representation in each layer and the sensitive group, and we try to find an upper bound of this aggregated information. Okay, so our many terms, I'll just show some related terms. First one is the delta. What the delta says is it equals to mu0 minus mu1. Here we focus on two sensitive group case. Okay, and we can see that this delta basically says the mean of the representation in each layer matters. Okay, the mean of the representation. What basically it says the data matters. Okay, the feature vectors matters. Gamma 1. Okay, here it says that there's a lot of notation. If you see a chi, it means cross group. If you see a omega, it means within group. What it basically says is the population of the nodes with or without inter-edge matters. Gamma 2. Okay, but gamma 2, the D denotes the degree of the nodes, either inter-degree or intra-degree. Basically, it counts how many neighbors a node has within or cross group. Gamma 2 says that the ratio of inter-degree and intra-degree matters. Okay, there's a lot of math, but the take-home message is the feature vector distribution of feature vector matters, the population of nodes matters, and the intra-degree distribution matters. Okay, specifically, if you can see if all the inter-degree and intra-degree are equal with each other, okay, every node has the same number of within group and cross group neighbors, then this term will equal to 1/2. Henceforth, gamma 2 equal to 0. So that to answer the previous question, in the sense that we actually do not focus on whether there's more inter-edges or inter-edges, this term will still show up. Okay, so now we have analyzed these three terms, now we can design a more disciplined technique to augment the data. Okay, the distribution matters basically says that we should sample the features that their distribution are closer to, are similar to each other, which leads to a feature masking scheme. And this says, gamma 1 says that the node population with or without inter-edge matters. So then we could use this information to sample the node population to make this term smaller. Gamma 2 says inter and intra degree matters. Basically, who are my neighbors matters. Then this leads to design edge augmentation schemes. So here I will skip the details of the augmentation design, but I can go over them in the end if needed. But the basic idea is using these three terms to sample the features, nodes, and edges in order to make these three terms smaller. Okay.
Ini, I have a question. So, so clearly when the issue is with representation bias, which is the example that you have, right?
Mm-hmm.
You can use sampling to compensate for that. What if what I'm trying to learn is a function of the amount of edges? Okay, let's say node centrality is the leading feature for determining a node classification, right? What row this node has. So then bias is not only expected, but it's something that you need to, it is something you need to learn, right? Then what?
Yeah, absolutely. So what you are saying is that is it the question that I want to learn the node centrality, or I want to make use of the centrality, that the centrality is a useful term for my learning, feature for my learning?
Either.
I see.
I don't know which one, but yes.
I see. That's a great question. So you are right that first of all these techniques that we are using will necessarily sacrifice the overall accuracy or overall utility. Okay? And now the question, but in general, what we want to do is to preserve as much as utility as we can, at the same time reduce the bias. But I understand your concern, and that is exactly why we later develop a different algorithm, because as you mentioned, that if we directly do data augmentation, then whatever we throw away, we will not be able to get it back. And we are not doing this augmentation in a way that we are aware of whatever learning task we are going to do. Yes, so that is indeed one of the problems, and motivates us later to do more data-driven algorithms so that it can actually take utility into account. All right, so some additional experimental results. And again, we use the node classification in this task. Okay, and we can see, first of all, the grace is the bias agnostic counterpart of the framework in the sense that grace is a graph contextual learning framework. What they are doing is a random sampling and a random feature and random edge sampling that are fairness agnostic. What we did is just to change their augmentation design. That's why they are the natural baseline, while these Fairwalk and GCA Nifty are fairness aware baselines. And you can see again, our framework always improves the baseline. In addition, just to mention that there are additional learning tasks. So we also carried out link prediction tasks. And similarly, we tested the performance on link prediction tasks with their corresponding statistical parity and equal opportunity measure. And you can see that the fairness-aware edge deletion arguments indeed provide a better fairness metric while comparable utility. And in addition, I want to mention that this, even though our analysis has shown a analysis based on two sensitive groups, this experiment is based on multiple sensitive groups. Okay, so it can be generalized. Okay, so just a brief summary that we designed fairness-aware adaptive data augmentation scheme. We provided theoretical analysis and provided extensive experimental tasks. And next, what we have already observed the analysis says that distribution matters, and we already seen that the data distribution from each sensitive group. Well, previously we see that we have augmented the data mainly on the graph structure side. Okay, now what we are doing is, since we see that the distribution of the two sensitive groups matters, then the question is, can we just directly shift the distributions to reduce this discrepancy? Okay. This motivates us to look at the graph normalization data. Okay? And the graph normalization, basically, it is just an additional layer similar to batch normalization in general machine learning. It is just introduce an additional layer, normalization layer in the graph neural networks. I need to mention that different from the normalization, you may imagine that I just subtract the mean and divide it by standard deviation. What is different is that this introduce alpha I, beta, alpha j, beta j that are, and the gamma j, they are learnable parameters. So it's not a normal sense of normalization, it's a learnable normalization. Okay, it has been shown that normalization really helps neural network and the graph neural network to converge and improve the generalization as well. Okay, so now the key idea is, this normalization needs to really shift or change the distribution of representation in each layer. And we say that the representation distribution matters. Okay, so now instead of applying one normalization layer, uniform normalization for the entire graph, can we apply group-wise normalization? Okay, so that's what we did, is we apply normalization individually over different sensitive groups. Here, N, it denotes the sensitive group label. Okay, and the normalization is applied after linear transform and before activation. So here, it acts as a preconditioner, and henceforth, it actually can be theoretically proved that it reduces the eigengap and provides provably faster convergence for graph neural network. In addition, since the normalization is applied before activation, one might be questioning whether this normalization will really be effective in changing the distribution of the representation, which is what we want. So now the question is, what is the effect of this M norm on the representation distribution? So what we can see is that, what we can show is that by doing the group-wise normalization, we can actually show that mean and the standard deviation of the representation we are manipulating is upper bound of the actual discrepancy in the original distribution. Okay, here what L denotes the Lipschitz constant of the activation function, and as you may know, most general activation function like ReLU sigmoid, their Lipschitz constant is equal to 1. So this is a quite tight bound. Okay, and this motivates us to say that, note that the notation is a little bit complicated, which wherever there's a bar, it means something that we can manipulate. Wherever there's not a bar, it means that something we want. Okay, so we add regularizers to wherever there's a bar there, because this is what we can change. And this, how we can change it, is this mu and the standard deviation can be expressed instead in terms of a normalization layer parameter. Remember that I said that it is not a normalization that we just directly apply. It is a normalization is actually learned from data. Okay, it's a data-driven approach. So that motivates us to add these two terms as a regularizers, so that when we are actually doing the neural network training, these regularizers will force the distribution to be closer. Okay.
How does the normalization you mentioned in the last slide? The normalization you mentioned here is the same as the one you mentioned last page.
Yes, exactly. The normalization I mentioned here, what I mean, mu and the mu bar, mu 0 bar and mu 1 bar are the mean and the standard deviation after normalization, where the normalization layer is indeed what I mentioned here. But when I use the M norm, I just use the separate normalization terms. I did not try to bring the distribution closer, right? So this just says I apply a different normalization layer, but whatever their parameters they are, it will be learned by themselves. In this slide, what we mean is that because this normalization has a learnable parameter. Remember, I mentioned that these are all learnable parameters, not that what we assign. So when we are, so these will be updated during neural network training. Henceforth, by adding the regularizer, I can try to force the normalization parameters to be learned in a way that the distribution are closer. Makes sense?
And how would the normalization you proposed in the last slide relates to the original one?
You mean graph norm?
Yeah.
I see. So the key difference is the N here. What it says is that the normalization I applied to each node or each representation would be different if this node is from node N or node 1, this node is from group 1 or group 2. Okay, so the key difference, again, you can see that the only difference is with or without N. Here it says that I just train a normalization layer for the entire graph. What it says is here, I should be aware that the nodes are from different groups. Henceforth, I may want to shift their distribution in a different way. Make sense? Any other question? So, of course, experimental results on node classification, and due to the limit of time, you should be convinced that it works because we have already published it recently. Otherwise, it would not be published. Okay, so but what I want to go a bit faster is here we remember I mentioned that normalization acts as a preconditioner, and we show that theoretically it provides faster convergence. then when no norm is utilized, here we experimentally show the convergence rate for graph normalization. And we show that it is indeed still faster than the when no normalization is applied, and similar to the graph norm. Okay, the difference is now we are fairness aware. Okay, briefly recap. We have developed a fair norm, which is a unified normalization-based framework to reduce the bias and improve the GNN convergence. And we provide theoretical guarantees for faster convergence. And the fairness regularizer are designed based on the analysis that I presented in the previous part. And they are also trainable. We train the normalization parameters in a data-driven fashion. And next, I want to quickly talk about this part. Is you can see that previously, graph neural networks, I told you that we are doing mean aggregation, we aggregate information. But the next question arises is that even though we are given a graph, some may be really effective connectivity, some may not, right? So, but the graph neural network simply doing aggregate the information from the neighbors, and you can see that I just sum them up and do the aggregate. Okay, but then this means that most GNN structures assign equal weights to all neighbors. However, this may not be the best idea, and as you may know, attention is all we need. So attention framework has also been used in graph neural networks. Okay, which basically says I learn attention weights, which indicates the importance of neighbors. Okay, and it works like this. There's a lot of math. The only thing that I want you to focus on is you can see that this is a weighted sum. Okay, and the alpha ij are calculated based on the representation. So now the problem comes when you pay attention according to the representation, you know that if the representation has bias, you will necessarily lead to more bias because it influences your attention as well. Okay, so henceforth, this leads us to the next framework is to first do some analysis to see what attention framework will lead to. A lot of math here again. Let's ignore all the other parts except for this part that is in okay, because other are representation distribution. Here is the part that is relevant to attention design. Here alpha chi, meaning that the total attention I assign for two inter edges, two cross group edges. And as you may know that they sum up the total attention I pay attention to cross group and within group sum up equal to 1. Okay, and here R1 chi and R0 chi denotes the node population, the difference in terms of node population. Okay, some ratios. Okay, so henceforth, this term is a guideline for us to do fairness-aware attention design. Okay, so now, as you can imagine, when I have an upper bound, now I just reduce this term. Okay, and the problem is convex, so I can actually solve it with closed form solution like this. So what it says now is that in addition to original design, what I did is if the two nodes are in different sensitive group, I weighted it, I multiplied it with alpha chi. Otherwise, I multiply it with 1 minus alpha. It's a reweighting of the original attention that you are assigning.
Wait, so now you only have 2 attention weights? Or is the softmax typically your attention and you're reweighting the original attention?
This part is the typical attention.
Okay.
That's why this has IJ.
Okay.
Okay, so experimental results. We use a 2-layer GN and node classification task, and we can see that this fair GAT is a fairness-aware graph attention network. indeed provides a similar utility again and a much better fairness measure than the alternatives. In addition, as you can see, the fairness-aware design in this case is just a reweighting of the original attention frame. Okay, so the computational complexity is not increased a lot. So we see that the runtime in each epoch, compared with the original GAT, is indeed only a very slight difference, and it's much faster than other alternative arguments. At the same time, it provides a better fairness. Okay.
What do you mean by runtime? You mean during inference or?
It is a runtime in training. It's the training in each epoch. Okay, just to conclude. So in this talk, I provided a theoretical analysis for source of bias in multiple GNN layers, including the traditional GNN as well as the graph attention layers. And we provided a different fair model design through augmentation, normalization, and attention design. And just to mention that the normalization and the attention design would kind of address the question that Professor Liu mentioned, is that it is a more data-driven approach in the sense that we are now adding it to the objective function. So if the original problem is more related to node centrality, then this will appear in the objective function and will be resolved. And actually, experimentally, we do see that the normalization and attention design works better than the augmentation, because once you augment the data, you just throw them away. It will not come back again. Okay, and it can be applicable in different stages of learning, also pre-processing and in-processing, as you can see, and they all provide efficient solutions. We provided experimental results shows improvements in fairness with similar utility. Okay, here are some related works, and we are also gonna present this as a part of our tutorial in KD in August. And I should give the credit to where credit is due. My students who did most of the work, and questions. Thank you.
Questions from the room and from the Zoom attendees?
I have questions may sound a little bit deviated. You like in this talk you're talking about we have a graph and the sensitive classes are provided. So is there a way that we can learn or estimate the sensitive classes from a structured network?
That's a good question. Yes, there are ways, and I have the existing works which says that the sensitive attributes are known or are unknown or partially known. So we need to first learn the sensitive group and then go back to the mitigating it. But yes, you're right. In this framework, we assume they are known, but it would be an interesting.
Yeah, thank you.
Other question?
Yeah, so this method that you use where you are renormalizing the graph, can you generalize this to other settings besides graphs? Because it seems like with the data augmentation, it seems like that requires it to be a graph structure. It seems like the idea of basically moving the distributions of each class, it seems like you could do that on more than just graph structures.
Yeah, absolutely. I think that even when there's no graph structure, it would still work. Basically, no graph structure says that each node is an independent node by itself. Yeah.
But there like other structures, like if you have like a manifold, or if you have something like I don't know, something more general than a graph, like, could you come up with a re-rating scheme for that as well?
So we haven't done it, but I think the normalization scheme itself, you can see it does not actually, it does not rely on the graph structure itself. It is only related to the sensitive group. So I would think that it could be directly applied, though I'm not sure about the convergence aspect, because when we do the convergence analysis, we did use the graph structure there. But the normalization operator itself is not dependent on the graph structure. It is just the distribution of two groups. A good observation. Other questions? If not, go ahead.
Do you have any analysis on the trade-off of the data augmentation and the fairness? I mean, like when you add or delete edges, you will like destroy or the graph structure. So do you have any like the analysis on trade-offs? Because you only present the experiment show that the fine accuracy is not that bad, or like similar utility. Do you have any theoretical analysis on that?
Okay.
I'm just curious.
I don't have an exact theoretical analysis on that, but for fairness-aware problem, you can see that if I just ignore all the graph and ignore all the feature vector, it will be absolutely fair. So if I just ignore, you can see that when I say nodes should have similar number of inter and inter edges, when I set all of them as 0, it will be absolutely fair. So, but in terms of utility, I don't have an exact result. It's also because we are based on unsupervised learning tasks. So we don't know eventually we will be using node classification or link prediction. Does that make sense?
Okay.
Well, let's thank the speaker again. I'm going to end this one here.